Hi, evening. Welcome all. Thanks for coming to our session on building enclosure engineering, and a little bit of housekeeping before I introduce Peter. Bathroom is just out there on the right-hand side. RAB numbers there for architects there. Just fill in the form, thanks. Otherwise, help yourselves. But a big thanks to Peter for coming to talk with us there this evening. Peter has done this for us in the past. I can tell you firsthand he's entertaining and great to listen to, and a shitload of experience there. Background Canada and weather tightness history there as well. Yeah. So I think it's fair to say he's seen it all, perhaps, or a lot, and a lot.
I haven't seen it all.
Okay. And if you've got any questions in the room during the discussion, feel free to raise it. Some of the bigger ones we may leave to the end to get more into the nitty-gritty. But thank you, Peter.
Thank you. Awesome. So that's me. I'm ready to go. All right. Hello. I'm going to speak right into the camera. Hello. How are you guys doing? Welcome. As Kevin mentioned, I'm Peter Raimondo. I come from Canada. I come from the Auckland of Canada, Toronto, downtown Canada. It is a big city, 6 million people. Who's the guy with the accent? That's me. I have a Canadian accent. Got here a little bit too late to shift my accent, I think. Also, I'm kind of stubborn sometimes, so could be that as well. But as you can see here, that's Toronto. There's a tower that looks kind of like the Sky Tower. It's not. It's the CN Tower. But it is a very, very large, telecommunications tower in the middle of the downtown area. You can see ice on the lake over there, top left corner. You can see it in the summer down bottom left. That's my University of Toronto that I went to. That's me hanging off the sides of buildings. Those are my feet, 30 stories down. On a swing stage, poking at things, spraying water at things, trying to find leaks and condensation and other things. And as Kevin mentioned, like I've seen a lot. I haven't seen everything. I can't claim that I've seen everything because, I have a rest of my career to go through. I hope there's going to be some new things. But I have seen a lot, and I have seen very cold temperatures, like Toronto goes down to -40, goes up to +40. So you get a big swing in temperature between winter and summer. So whenever there's problems with the building envelope, the building enclosure, the outside of the building, there is, those problems tend to show up pretty quickly because of the fact that it goes down to -40. So what's an envelope? Not the mail kind, not the mailroom kind, but the building enclosure. Everything that separates the inside from the outside. So that's roofs, that's walls, windows, underground tanking, all the junctions in between, all of the different things. And that's what I concentrate on. And a lot of times I get asked these questions like, what do you do? What value are you bringing to a project team? We generally only get put on a project if it's a larger project, a more complex project, or at least historically that's what that's been. But there's so much more that we can do, even for buildings that don't require our services, and council's not asking us to be there. But we do, we engineer the things that separate the inside from the outside. Like I said, walls, windows, insulation, roofing, membranes, below-grade waterproofing. But the key thing is all the junctions between all those different things, because you'll get details and data sheets and things like that for a roof, for a window, for a cladding, for an insulation, for this, for that. But they don't usually talk about what happens when you have to transition those to other things at adjacent assemblies. So we concentrate on those things mostly, act as a translator between architects and engineers. A lot of times you guys are asking for certain aesthetics, certain things to look a certain way, but the structural engineer doesn't really care. The mechanical engineer doesn't really care. I try to care. I try to, translate what that means, and whatever we have to do to engineer that to be able to work structurally, mechanically, or however, trying to translate what the design language might be, or what the, massing that you must, keep is, or the lines that have to line up with each other. Because a lot of times engineers aren't looking at that because that's not necessarily their job. We liaise between different engineers and consultants, trying to make sure that everything is kind of working together, because the enclosure, the envelope, the exterior of the building is affected by the structure, by the aesthetics, by the mechanical systems, by all the different engineers, acoustics, geotech, like all the different things. We have to kind of liaise between all of those because we're designing something that has to work with all those different constraints. A convincer of councils and reviewers. Yeah, we generally are brought on projects to write a compliance report, to explain how things comply with code. Sometimes it's easier than other times. Sometimes it's very easy, but sometimes it's kind of a bit difficult, especially if you're going outside of the norm, especially if you're going over and above the requirements of code. That is sometimes when councils get a little bit confused because they haven't seen it before and they haven't seen every situation and they don't necessarily have like a framework to analyze. We'll get into that. An investigator of leaks and condensation, that's what I was doing when I was hanging on the outside of the building with my legs dangling on a bosun chair and on a swing stage. Investigate leaks and condensation, try to figure out what the root cause is and try to figure out a solution that will avoid those root causes in the future. Energy modeler, sustainability consultant can also do that. Enabler of bespoke and unprecedented designs. That's another big thing that I love doing. That's what gets me excited about doing my job, is working outside of E2AS1 details, working outside of the standard manufacturer details to do something a little bit more interesting, a little bit more beautiful. Recommender of good assemblies and details. Yep, that's pretty easy to understand. And a reviewer of data and reports. And so, when you're looking at a certain type of assembly, a certain product, a certain component, something like that, we review that to see, is it going to work in the context of this building? Is it going to make sense within all the constraints of all the other consultants and whatnot? So, yeah, we do a lot of different things. We wear a lot of different hats. How did I get into enclosure engineering? I got this question when I did a presentation at Victoria University in Wellington, because it was a bunch of architectural students and they're like, how do you get into this? And so, yeah, luck and whimsy mostly. It kind of just happened. I started in civil engineering. I worked in construction. I was up at 5 o'clock in the morning, on site pouring concrete and tying rebar. Obviously didn't like that because it's just too early in the morning and just, not great. Got into forensic engineering after doing a bunch of, Europe traveling and working as an a cappella singer and doing a bunch of weird things. Got into forensic engineering, which sounds really cool, but really it's just tearing things apart and figuring out why it leaked and why it burnt down and how to not make those two things happen again. Then after working a little bit in that, got into building science because one of my friends was quitting to go do a PhD. But yeah, got into the building science space, worked in Toronto for probably about 4 or 5 years. And then once I moved to New Zealand, everything kind of really took off because it seemed like there was a big gap in the market for the type of knowledge or the type of experience that I brought to the table. And everything kind of just really started rolling. And I think that was also because it was 2018. That's when councils really started asking for facade engineers, asking for, second or third party review, a second set of eyes on drawings to make sure that they're not going to be leaky buildings. So what do we actually do on a project? I kind of told you what is an engineer, a little bit more fluffy. But what do we actually do? We review drawings. We do markups on those drawings, help with the detailing. We can draw sketch details, or if you wanted to pay us for it, we can, do actual full 3D details. We don't usually do that because you guys usually have enough people drafting to be able to do that, cheaper than we would. But we suggest components and products that work together. We suggest different details that aren't like the typical ones to help you get a certain aesthetic or a certain visual language that you wouldn't be able to get with the typical details. Help you work outside of E2AS1. Investigate and remediate leaks and condensation. That's what I was doing in Canada. I also do that here. It seems to be less popular here. I feel like there's a level of acceptance of leaks and condensation issues that a lot of building occupants have here, which is okay. But I think a lot of people are asking for better these days. And so I'm getting called more and more often to do those kinds of things. Create a comfortable and efficient interior space. That's what we're all trying to do. The flavor that we bring to that is just talking about the different components. A window's a window, but not really. The frames are a little bit different. The glass might be a little bit different. We kind of explain those differences, those minute differences between the different types of components. We also, like I said, liaise with the mechanical engineer to make a nice, efficient mechanical system that works really well with the enclosure. We help mix aesthetics and functionality, mitigate risk of mold, check for air tightness. That I've been called about recently a couple times, designing for air tightness and then checking for air tightness after the fact. adding durability and redundancy, because the E2AS1 details are good for certain scenarios and certain situations, but when you start going mid-rise, high-rise, sometimes they don't have the same level of durability and redundancy that they could have. Answering RFIs, monitoring construction, kind of goes without saying, or kind of, it's self-explanatory, but the construction monitoring is the part that a lot of engineers don't really do a lot of. I know the structural engineers will come and check on, rebar, Rio, and formwork, and making sure it's all in the right place, the size and bolts, and everything's tight and stuff like that. But they're not necessarily checking every single thing. It's more of a spot check. Facade engineers typically, before I got here, as far as I've been told, didn't really do much construction monitoring at all, except for maybe 1 or 2 site visits. But we try to go like once or twice a month minimum to, make sure everything's going well, sort out any problems. But yeah, a lot of times people just think we get in the way and then write a report for consent. That is, less common of a belief these days. But when I was first starting here, a lot of architects, project managers, clients, any of the other consultants all kind of thought, like, what are you guys even doing here? Like, we never needed you before. Why are you here now? And so that's when I try to bring value to why I'm there, because, we're probably cheaper than most consultants because we have, a smaller scope of work. But that small scope of work is spread around the entire building to all the different components. So yeah, I try to explain that. But when it comes to site stuff, when it comes to enclosures, which is the part that I design, we oversee and request testing. That could be spray testing, pressure testing with a spray rack on the outside. That could be blower door testing for air tightness. That could be EFEM and sensors for membranes, for leaks through roofing and stuff like that. Adhesion testing, sealants and things like that. Mock-ups for window details, cladding details, transition, seismic joints, anything's bespoke. So that's all the general stuff that we do, but also just being on site on a regular basis means that the installers are expecting us to come. They're trying to do their best and not trying to guess. Because when you have installers on site just guessing how to meet your design intent, but there's no specific detail for that one specific corner junction, they tend to make things up. And sometimes they're very good at that, and sometimes they're very effective at that, and sometimes they have no idea what they're doing. They're just trying their best, and it's going to be a leak later on. So that's what we try to do on site. Questions to get you thinking. To the people online and to the people in the room, if you saw my presentation 2 years ago here, or at my Tulo Ed webinar that I did a few weeks ago, then all of these slides might seem very similar. What I say, because I don't have a script and I kind of just like stream of consciousness speak, I just kind of go. And so if anyone has any questions, if anyone has any concerns, if anyone has any specific things that they want to ask about, please feel free to interrupt me. Even if you're online, send it through and it'll come in online and I'll be told about that. But to get you thinking, what kind of house did you grow up in? I don't want answers necessarily, just kind of picture it. Was it an older villa, weatherboard, and metal roof? Was it like a brick and tile house? Was it fully detached? Was it semi-detached? Was it a townhome? Was it an apartment? Did it have aluminium windows, wood windows, UPVC windows? Did it have windows at all, or was it just open louvers on the walls? Were you comfortable? Were you comfortable in the summer versus the winter versus summer? Shoulder seasons may be comfortable, summer and winter maybe not. Do you have to wear a jacket inside? Do you see your breath when you wake up? Do you have to wipe the windows every morning because there's condensation on them? Just little things, just things to think about. And then the last 3 questions, these are more questions about just what do you maybe have a prejudice about? What do you have a preconceived notion about that may or may not be correct? Do roofs always leak? I feel like eventually everything always leaks personally. But are membranes better versus a metal roof? Are metal roofs ever leaky? A lot of times long run metal is pretty good, but it does have condensation issues if those aren't dealt with. Membranes can be risky if they're not installed properly, or if the right one isn't chosen, or if it's not detailed properly, if it's not installed properly. There's all kinds of things. Can you have a dry basement? This is one that I run into a lot. I feel like I can design and construction monitor a dry basement. But there's a lot of people who believe that's not possible, and so a lot of people want to put a moat around the building, and maybe put some waterproofing on the walls, but have, lack of any water pressure coming through that wall. That is a good way to do things. It's a very expensive way to do things because you're building two structures now. But it can work, but there are other ways to make it work with membranes that are designed, installed, etc. How does the building code work? I'm going to skip through most of this. Everyone kind of knows. There's building act, there's building regs, there's building code clauses, there's acceptable solutions and verification methods. I feel like everyone's probably very familiar with all this. Building code, there's A to H. There's, a bunch of them. Most of them have multiple numbers except for H. H is just one. There's only one H for some reason. Maybe they'll add H2 later on. I'm not sure, for like overheating possibly. Who knows? Anything's possible. But you got acceptable solutions. You got verification methods. Acceptable solutions are the prescriptive ones. Verifications are descriptive. How do you prove that it complies? And then alternative solutions, code mark, multi-proof appraisals. They're not laid out in the code, but they're sometimes used. Depends on the council person that you're talking to, depends on who's reviewing your package. If it seems confusing, it is. It's very confusing because there's so many different pathways to comply that there's not really a good way to say this meets code. You can say it meets code, but then someone can interpret it differently, or there's all kinds of weird compliance pathways and different things. All those things that I've listed: producer statement, brands appraisal, code mark, CPEN, licensed practitioners. That's the only real pathway, code mark. That's the only one that the council is required to accept. Everything else is just, yeah, we'll probably accept that. It's more just like strengthening your application, essentially. But because it's so confusing, because it's kind of all over the place, because there's no specific exactly, if you follow these steps, you will get your consent. A lot of people just usually default to the easiest option because it got through last time. We didn't have to wait a long time. We didn't have to answer a bunch of RFIs. And that's generally what people default to, which is exactly why it's very difficult to go over and above, why it's difficult to kind of go anything outside of what's generally expected. This fact is very interesting to me, the fact that councils ask for producer statements, even though they are not in the Building Act. They have no legal standing whatsoever, but everyone just believes that they're important, and we all act as if they are important, and therefore they are important, because we all believe so. But I've had my PS1s not thrown out, but they say, oh, well, just because you have a PS1 doesn't mean we're going to give you the consent. And it's like, yeah, okay, cool, I guess that's how it is. So what we generally try to do is try to just work with council and just give them what they want to hear. So we usually follow the AC 1827 document. Has everyone seen this? That seem familiar? Everyone read through that? Cool, great. Just as a simplification, we generally like to go through pathway 2. That one down there, which is us being involved in design. We write a PS1, we give that PS1 to council, and then we're good to go. The other one that we also go through is pathway 4, when we need a separate facade engineer or enclosure engineer to do a peer review of our work. That's perfectly fine. It's just if it's a taller building, a much more complicated building, then that's when council will ask. But the older way to do this before I got here was pathway 3, which is a PS2 peer review. We would do a peer review on generally architectural documents, whatever they might be. That was kind of the standard and how people did things, pre-2018. I feel like most of the facade or enclosure engineers have, moved towards doing PS1s. I think it makes much more sense because if we're involved in design, we can help you with the design, we can make suggestions, we can help you detail, help work outside of acceptable solutions, help you work outside the typical way that you'd always done things. And then still get you a consent. And we're responsible to answer those RFIs. We're responsible to go to bat for you with council. Whereas with a PS2, you're showing us your documentation towards the end of design, and then we mark up things, and then you have to go and change things. That'll add another 6 to 8 weeks onto the schedule, and then we have to kind of argue and negotiate back and forth, whereas if we're just doing it during design, it's all done, and then it's a really quick process at the end. So back to the title of this, compliance versus doing it right. So basic compliance for the exterior enclosure, which is the thing that I do, which is the thing that I concentrate on. Really, you're doing B1 for wind loading and seismic loading. B2, durability, 5, 10, 15, 50 years, depending on the component. I forgot the 50 there for some reason. E2, external moisture. prove it. Usually that's acceptable solution. It can be an alternative solution, which is what we generally do. We'll write a whole compliance report to explain how everything works, put stamped drawings in the back saying we checked it. And then H1 energy efficiency, that one you have to comply with. Do councils ask for H1 reports usually? They do now? Okay, it's more asked for. Okay, cool. Because previously, I don't know, there was a lot of projects that I saw that didn't have any H1 reports, and I guess they were just maybe just checking online. I don't know. I don't know how they're figuring it out, but yeah, that's basic compliance. But we try to do a little bit more than that because you're paying us a bunch of money. We might as well spend it wisely. We might as well do something with it. But yeah, it depends on the project, depends on what we're hired to do. But what we try to do is that flow chart at the bottom. It's a little bit small writing, but we'll have the pre-design phase where we'll look at your general, resource consent drawings or preliminary drawings, make some suggestions. You can make windows a little bit smaller if you're worried about overheating or something like that, or make some suggestions about little small bits and bobs. The design phase is where we're doing a lot of, like I said before, suggesting assemblies, reviewing documentation from suppliers, eventually end up writing a compliance report, drawing markups, things like that. And then in the construction, you can see the construction phase is pretty long as well. We kind of made it look like that because that's generally the timeline that you'll see on projects. We'll respond to RFIs from the council, from the contractor as well, respond to value engineering type stuff where the contractor comes in and says, hey, can I swap this for that, swap that for this, swap that for that? And sometimes that's when things kind of break down. But we try to make sure that we're asking the right questions, checking the right things, and making sure you have equivalent stuff as opposed to a downgrade in quality. Investigations for retrofit and remediation projects, that'll usually come before or during the pre-design phase. So if you have an older building that you're retrofitting or an older building that has to marry in with another building next to it or something like that, or an old building that you're building a gigantic building around and it all has to transition, those kinds of things will go and do investigations of that existing building to figure out what needs to be detailed, what would be the risks during design, what would be the risks during construction, things like that. And for us, just to plug specifically OBSF, Oculus Building Science and Facades, we cover the entire building enclosure, including roof, below-grade transitions. That is becoming more typical, but it was not typical pre-2018, pre-2019. And there are still, facade engineers in the industry that really concentrate on facade engineering, which is vertical surfaces, structural stuff, curtain wall and things like that. And they'll usually tag out of roofs, tag out of below grade, tag out of indoor pools, things that are a little bit more complicated that need a little bit more complex analysis. So we do that as a standard. That's like what we always offer unless you specifically request us not to for whatever reason. We try to work pragmatically and practically to solve design issues, try to fix things. If there's a mistake on site, try to fix it without having to rip apart the entire building. Bridging gaps between details and manufacturer manuals, suggest assemblies that designers might not have thought of. Construction monitoring, I've made that in capitals just because it is important and it's something that is only becoming popular now. I've already talked about this, but yeah, we review shop drawings, first install, answer questions about buildability, help kind of massage the details a little bit. If the contractor has a very specific way that they want to build something, we'll make sure that it still meets your design intent, but is also, meeting whatever they want. Agreeing that the installers understand the procedure. We do spot checks. Sometimes there's a different crew that comes in from the installers. We'll go and we'll make sure that the new crew knows how to do everything as well. Observe testing, request testing, observe repairs. CM3 observation is usually what we're doing, so once every week or two. We don't sign off on things. We don't approve scaffold removal. We don't observe everything. We don't instruct anything, because that's usually not our contractual, scope to do that. We can make recommendations. We can say this is built very badly. It should get fixed, but then someone else who is in charge of the contractor has to be able to do that. So just wanted to put that at the bottom, just in case there was an idea that, you're working with us on a project or working with another facade engineer on a project. We don't sign off on things. We don't approve anything. We don't observe anything. We look, we give information, and then everyone else has to make good decisions from that. So above and beyond, as opposed to just base compliance with code, things like tanking and waterproofing. There's no standard in New Zealand for tanking and waterproofing. So we usually look at the BS 8102. That's from the UK. And we use that to have the conversation about how dry are you expecting this wall below grade to be, and how do we design to make it happen. There's references to condensation in the code, but there's no requirement to address interstitial condensation in E3. Brands came to our building science seminar, building science series, beginning of March, and they were saying that they are working on an acceptable solution for E3 and then an acceptable solution for G4 as well, to help tie those things together. I'm not holding my breath, but I'm hoping that it will happen, and it will happen soon, because right now, I've tried to address interstitial condensation, things like regular walls that have, a sheathing board on the outside will have condensation on them during the winter, inside the walls, and then we are just designing it such that if you use heating on the inside, it'll dry outwards. But having that conversation is difficult because a lot of people don't want to hear about condensation. Councils especially do not want to hear about condensation. I've gotten my hand slapped a bunch of times because I put condensation risk into a report, and they don't want it. They don't want to hear it. They don't want to talk about it. So if there's going to be an acceptable solution, then that'll be great because then I can have a nice, easy conversation, and we can be comparing the right things. A general belief that windows and passive vents are sufficient for ventilation of interior and attic spaces. So, in G4 of the code, if you have a window that is 5% the size of the floor area of the room and it's able to be opened, you get your ventilation check mark. But does that actually ventilate the room? Maybe, if the wind is pointing the right way and it's open enough times, but it doesn't actually necessarily work. And the ventilation part of the code doesn't specifically say how much, parts per million of CO2 have to be in the air, doesn't say a specific temperature that needs to be achieved, doesn't say a specific relative humidity that needs to be achieved. So there's a belief that these things work, and you get the check mark, you get the acceptable solution, but it only sometimes works. It only works if the weather's cooperating. And so, yeah. When we're working on a project, we try to have these discussions and see if we can design a little bit over and above. Put, balanced ventilation, continuous ventilation ideally, or if you're going to be using passive vents and windows that only open a certain amount, maybe having a fan that is on kind of all the time, low pressure, just to suck a little bit of air through, just to force that ventilation to happen instead of relying on the weather. So another one is general distrust in membranes due to material or install. I've seen a lot of problems with membranes. I get it. There's a reason why people believe that they are risky. I get that. It makes sense. But it doesn't mean that they always break down or they never work. It just means that it's a little bit more complicated and there's a little bit more nuance involved and a little bit more design involved. External insulation, I try to get it on a lot of buildings. It does not have an acceptable solution, so it's rare. I've gotten maybe 10 buildings or so far, which seems like a lot, but compared to how many buildings there are in this country, it's not super popular. And there's many missing items in H1, including thermal bridging. So with all these things in mind, you have to kind of go a little bit over and above instead of just getting the tick box. Or just get the tick box and just know the difference. Just know that you're just getting compliance and that certain things may work, certain things may not. So, acceptable solutions, do they work? H1, as an example, you might have seen this already. I'm going to go quickly through it. Are you comfy inside always, everywhere? I'm not. I try to make my house pretty comfy, but that's because I spend money on heating and ventilation year-round. The heater turns off during the summer and shoulder seasons, but winter, I just leave it on a thermostat year-round, like for the whole winter. So yeah, acceptable solutions, do they work? Not really. They're a good, easy way to get a tick box, but they don't necessarily get anything done. But the old H1 R values, they went up. Did you guys notice a difference? People are building more. People are spending more money on insulation. People are installing more insulation. Has it fixed the problem? Probably not. It has also accelerated the noticing of problems, such as overheating. We've seen it all in the news. Insulation doesn't cause overheating, but it traps in heat. And so if you haven't designed the building to avoid trapping in that heat, then the insulation will do a very good job at doing that for you. So yeah, it doesn't create heat, it just slows the transfer of heat. Upping the insulation can keep it in, but it has to be, you have to use heating to make it warm. So in the winter, just having insulation, but you leave all the windows open and all the outside air is inside, it's not going to be warm. But insulation will keep the heat in if you use the heat. So schedule method isn't the best choice. They're getting rid of it anyway. That's great. I love that announcement. I don't know any of the particulars around it yet because it was just an announcement without any sort of framework. But they're saying no more schedule method. Don't just get your tick boxes for the R values. Now you use calculation method. It's not really that much of a difference because basically you're just saying this is for roof, this is for wall, this is for slab on grade, this is for other floors, this is for total wall area. These are the schedule R values, and you can kind of mix and match with that formula. So it'll do a little bit better, but it won't necessarily solve the problem because you're not checking all the things. So what needs to change to make H1 work? Well, all the things that are listed in black there. All the pink ones, that's already included in code, but things like thermal bridging, not required. There's some language in there saying when you're designing a wall, you have to get a construction R value of that wall as opposed to just the insulation R value, but you don't have to think about the slab edges, you don't have to think about the corners, you don't have to think about a lot of the other install thermal bridges like the window to wall junction, things like that. Don't have to think about that. Vapor control, definitely don't need to think about that. That's not anywhere in the code. Envelope air permeability levels. It says, think about air tightness. And so if you think about it, you get your tick box, you're good. On-site verified blower door testing, well, you can think about the air tightness and design something that you think is going to be airtight, but then if you don't test it on site to make sure that it got built that way, are you getting air tightness? Maybe, but maybe not. Cooling demand and overheating potential limit. So solar heat gain, in H1, in the acceptable solutions and the verification methods, it says consider overheating. These are some strategies you can use to consider overheating. It gives you strategies, it says consider it, but you consider it, good, tick box, done. That doesn't actually, necessarily mean that you're going to get a good outcome, but you got compliance, which is cool. These ones over here are also particularly not great. Thermal comfort, so there's no specific setting in the building code that says you must maintain a certain temperature, between a certain temperature, a certain relative humidity, or between a certain relative humidity. I know the tenancy tribunal, sorry, what am I thinking about here? Healthy Homes Act, that's the one, thank you very much. Healthy Homes Act says that you have to have a fixed heater, so cool, that one thing, if you want to rent the house, then you have to have a heater somewhere, cool, that's nowhere else in the code. There's no temperatures except for childcare and elderly care has to be above 16 degrees, but there's no maximum. Relative humidities, not considered whatsoever. Condensation control, also not considered, except for in E3, in the functional requirements and the beginning preamble, not the acceptable solutions, not the verification methods. Those things say make sure. I'm paraphrasing, obviously. Make sure moisture gets out and doesn't damage anything, but it doesn't really tell you what to do or how to do that or how to prove that. So, lots of fun. So yeah, there's a lot of missing things. These black boxes are what we try to design or design away during design. But because it's not required by the code, we can make suggestions, we can make recommendations, we can have lots of conversations. But if the client ultimately doesn't want to pay for it or doesn't want to pay what they perceive it's going to cost, can't really do much. So we're asking for your help, I think, it's the general call to action there. Use modeling to check. Green Star, Home Star, Passive House, LBC, Living Building Challenge. Energy modeling is often a requirement, as we were discussing before. Now that money is a little bit tight, those are the first thing to go out the window. We don't care about Green Star, we don't care about Home Star. I've had a bunch of projects that were supposed to do all those things. They've all said, nope, we're done. We're just trying to do it as cheap as possible. So with modeling, if you can get the client on board with some energy modeling, you can advise best bang for buck, best value for money strategies to make things better. But they have to want to pay for the modeling to begin with, which is sometimes a hard sell. But if you can show them how you can kind of make good decisions for investment for CapEx versus OpEx. So spending a bit more now to save a bunch more down the road over the lifetime of the building, then maybe you can get it across the line. But some clients are stubborn, and that's okay. Everyone is their own person. Passive house is what we generally use for energy modeling. It's not the only way, but it's a pretty good way because it looks at all of those different things that H1 doesn't. Fun fact, if you have a 150 square meter house, you can heat it with 18 cats. You don't need any sort of heater inside there. You can just have your cats. You probably want to let them out during the summer so you don't overheat, but it's possible. It's pretty good. Has everyone seen this before? Has everyone seen things generated from Passive House? Yeah. Basically, this is the fun part right here. That's like the losses and gains, the inputs and the outputs. How does energy balance? And you just try to make those as low as possible, both of them, because they should balance, but you have to make them as low as possible. The bottom left over here is a Flixo model that's showing a thermal bridge at a slab edge between two windows. Just interesting stuff. Passive House checks on these other things. The condensation one specifically, you have to check for with your thermal bridging. How do I stop condensation? I feel like I've talked about this a lot, but I'll reiterate it again. Basically, you have 3 boxes of air, or 3 droplets of air, I guess you could say. This one's at 30 degrees, this one's at 20 degrees, that one's at 10 degrees. All of these water contents are the exact same volume of liquid water distributed into the air. So basically, the key is that if you have warm air, it holds more moisture in it. Cold air holds less moisture. If you take that warm air and cool it down, the percentage of moisture that it can hold goes up. And therefore, once you get down to the dew point temperature, 10 degrees from 30 degrees, is 100%. So you'll start to see condensation. Can we see some on? Yeah, we can see some on the glass over here. That's because the temperatures of those liquids are below the dew point temperature of the air inside this room. So what does that mean for buildings? Well, windows collect condensation, as you may or may not remember from wiping your windows possibly this morning. It wasn't that cold overnight, so maybe not this morning, but maybe tomorrow morning, because it's supposed to go down to 14 overnight, maybe. Use thermally broken frames, double glazing. You can use triple glazing if you want, but with the temperatures we have in New Zealand, usually it's not worth the extra money, in my opinion. But depending on what kind of outcomes you need, what kind of, if you need it to be particularly very comfortable right in front of the glass, then maybe triple glaze is what you want. But might not always be the case. Walls can get wet and rot with bad assemblies, make them airtight and vapor permeable, or use external insulation. The one thing that whenever I'm looking at a project, the first thing I mark up with a red pen is strap-in-line concrete. If you have a precast or cast-in-place concrete wall with timber straps, fluffy insulation, and gypsum board, that is so risky for condensation. And it's acceptable. It's in E2AS1. It's showed in the concrete manual, their SOP. It's a standard thing that everyone builds with. But if you've ever been into an older building and it kind of just smells, usually it's condensation in the walls, and usually you'll find that the precast ones tend to smell earlier than the rest of the walls. Because of the fact that you have a vapor permeable and not very airtight wall, the air at the interior temperature and relative humidity goes through that wall, touches that concrete, which is almost always below the dew point temperature during the winter. And it'll start to grow water inside there, mold inside there, and it'll just build up over years. Because it is so temperate and such a lovely climate here in New Zealand, especially in Auckland, it'll take 5 to 10 to 15 years before you'll notice, and you'll start to see mold anywhere. You start to really, really smell it, and it's just like very noticeable. But it happens from day one. So yeah, that's usually what I change. I change it to a very cost-effective, similar thing. Just use a different insulation and put the straps outside the insulation. Usually fixes the problem. Or put external insulation, but that's not always in the cards. Metal roofing iron, cold due to night sky radiation. Has everyone heard of night sky radiation? Maybe, maybe not. I'm not seeing nods, but okay, cool. So night sky radiation is when you have a clear night. I feel like it's cloudy today, but on a clear night, because the blackness of space is just open to the elements, any surfaces on the Earth will radiate infrared light, heat energy out into space. and that will make those surfaces up to 10 degrees, 5 to 10 degrees colder than the ambient air temperature. So if your air temperature is like 10 degrees, it could go down to 0 and you could see frost. That's why you see frost on nights that don't go below 0. It's because of that night sky radiation. So it's a thing that you don't necessarily think about because we never really needed to think about it because older buildings didn't have a lot of roof insulation, so you'd have a lot of bleed from the heat from the inside, keeping all the temperatures inside the attic nice and warm, and so then you don't get that condensation on the underside. But now that we put R6.6 insulation into our roofs, we're going to see it be a problem. I'm already seeing it be a problem. If you've ever popped your head into the attic, if you've just put new insulation, pop your head in. Just see if there's any condensation on the underside of the metal, underside of the underlay, maybe on the actual rafters, purlins, things like that. Yeah, poor ventilation, intermittent heat is bad. Use mechanical ventilation, put a heat on a thermostat. That's what I do in my house because I know that it works. It costs a little bit more money, but not as much more money as you might think because you're maintaining temperatures as opposed to letting things cool all the way down to 10, 12, 13 degrees, and then back up to 20, back down to 10, back up to 20, back up down to 10. So it kind of balances out. What do I do with this random info? It bother people. Have condensation conversations with people at parties and stuff like that. I do. I try not to because I see the eyes start to glaze over. But sometimes people want to talk about it. People really are really interested in it, and so hey, I'll do it. So yeah, some questions or some things. I feel like I talked about this last time a couple years ago, but we'll do it again just because it goes. It's important. Old houses didn't have condensation. Yeah, I agree. A lot of the time, the old houses didn't. But why not? What do those old houses have in common? What other problems might they have had? So, why not? Any hands? Anyone online? If you have any questions, yes. Sure. And so they were air leaky. You mean? Yeah. And so water blows through them. Air blows through them, dries things up. Sure. Ed?
Cold inside.
Oh yeah. Sorry.
They were cold inside anyway, just as cold as it was.
Sure.
Outside.
Could be. Yep. And so you're not getting that temper differential. Yep. Sure. Anyone notice those kind of tall bricky things that are standing up either inside or next to or above those houses?
Are we referring to the chimneys?
I am referring to the chimneys, yes. So all those old houses had a big fireplace, a big open fireplace, and people would generally have a fire going most of the time in the winter. Correct me if I'm wrong. I don't want to say things out of turn, but usually people will have the fireplace running, or at least back when they were first built, they might have. And those fireplaces, they first of all heat up the space, but also they provide ventilation because the fire is burning, air is being sucked into the fireplace to feed the fire, and then it goes up and brings moisture with it out the chimney. So you're getting dryness. Yes.
We've had one person in the chat come through saying drafty and no insulation.
Yes. And that's very similar to the answer we got in here. They were drafty and had no insulation. So insulation is great for us as humans because we want to be nice and comfortable inside the house. But putting insulation inside your assemblies makes the inside more comfortable, but it makes the outside of that insulation less comfortable. So if you have your weatherboard there that was uninsulated, and you have the heat from the inside going through, air going through, drying everything out, it all works. The second you go to add some insulation into there, sometimes things happen because that exterior, the inside face of that cladding could possibly be below the dew point temperatures of the air that's going in there, and so you start to get condensation on the interior side of those weatherboards. I saw an older house where they put that fluffy insulation where they cut a hole and they just dump the fluffy insulation in there. He put that in, and 2 to 3 years later started getting these weird brown drips between the weatherboards. And my thought is that there's probably condensation happening in there. Some water is, forming on the interior side of those weatherboards. They were painted on the outside, but not on the inside. They might be picking up some oils or some tannins from the timber and then starting to leak out. Not much you can do about it at that point, other than ripping out the walls and ripping out all the insulation and then just, bringing it back to normal. But there are ways to insulate these older houses that don't cause those problems. My old colleague, John Davies, has a parka wrap. Has anyone seen that? He's posted about it online. Guy from, he works at ProClima now. He used to work with us. Basically putting external insulation on the outside of weatherboards and then putting new weatherboards on the outside of that. So if you put external insulation, if you do get any dew point issues, if you do get any condensation outside of that insulation, it's outside of the building and it'll just drip right out. It'll be fine. So yeah, heating and ventilation, this is one of the things that I mentioned, makes a lot of problems go away. If you just add heat to the system, waste money on energy, you will probably cure a lot of condensation problems. But you also kind of need the ventilation. Ventilation removes moisture. Lower expectations. Things were just cold back then, and that was okay. No one had the expectation of being super comfortable inside. Also, things like this right here, that's something that is, exists in some houses that I've seen, but not very many houses here in New Zealand. In Europe, everywhere. Every window has a radiator under it, and that's great because it might be less efficient in terms of, energy use or heating use, but during the winter, you can crack open that window, a little bit of air will constantly flow through, will always be warmed up by your radiator, it'll absorb moisture, and then it can go find its way out elsewhere. So it means that you don't get a lot of condensation on windows. It means that you get some ventilation coming through that window and it doesn't feel drafty because it's being warmed up by your radiator. So yeah, these are things, old school things that worked. Not super energy efficient, but they worked. But here we're seeing a lot of overheating because we've tried to fix the problem by just adding a bunch of insulation to it. If you add insulation willy-nilly, you could cause a problem, especially if you have gigantic windows facing north, facing west. They'll collect a lot of heat energy during the day, and then you're trying to just pump it all out with crazy amounts of ventilation or with a really big air conditioner or something like that. It's a big risk that hasn't been fully closed in the code. So big risk with apartments, terrace houses, because there's a lot of rules for how big you can open those windows. You need to balance between the light and heat gain. It's much easier to keep the heat out, much more energy efficient to keep the heat out than it is to try to cool it with air conditioning after the fact. So these are all things that I'm sure you guys all know, but there are things that can be done to mitigate that overheating. Classic solution, big overhangs, like older villas, older cottages and things like that. They all had big overhangs, especially like out the outback of Australia, big overhangs. That's great because in the winter you get lots of light in through, but in the summer, because of the high angle of the sun, then you get a lot of shade. Modern solution, louvers everywhere. I've seen so many buildings and there's just like louvers on louvers, window surrounds and things like that. They work. A lot of times they're more for decoration than actual, solar heat gain. But if you can make them work for solar heat gain and cutting out that amount of sun that comes in, amazing, great. A complicated solution, operable exterior shutters. I've seen like ones that get, opened and closed by people, but other ones that are like motorized and move around at different times of day, different times of the year. Can do it. But a cost-effective solution is just changing out the glass, especially if you have a certain look in mind, and that's the look, and you can't add an overhang, you can't add a louver, you can't add a shutter. Good glass. And when I say good glass, I mean using a low-E coating or a tint, or both. But the thing that you want to kind of just make sure that you understand is the fact that not all coatings on glass are the same. Every one of the glass suppliers, Viridian, Metro, AGP, and I feel like there's another one that I'm forgetting. Woods? Yeah. So all four of them have like a standard option, which has an SHGC, a solar heat gain coefficient of like 0.7, which means that it's cutting out 30% of the solar heat gain, but it's allowing 70% to come in. What you want is something that's a lot more heavy duty that cuts out more than 50% of that solar heat gain. So the SHGC number being under 0.5 is, good. You can go down to 0.3, you can go down to 0.2 if you're adding a tint and a low-E coating together. But yeah, it's a cost-effective solution. Just switch out the glass. It doesn't cost that much. There is a premium, but not that much in terms of... Sorry? Losing light if you're adding a tint. If you're adding a low-E coating, even if it's one of the powerful low-E coatings, it'll lose a very small amount of the visible light, like usually maybe 5 to 10%, something like that. And you might see, if you're looking at two panes of glass side by side, the low-E coating one will look a little bit blue, a little bit green, a little bit purple. But there are different ones that you can choose, ones that look better, ones that look worse, ones that allow more of the visible light spectrum through versus less. Here in New Zealand, those four suppliers usually have 2 or 3 options, but they have thousands of options that they can indent from overseas because like the main manufacturers like Saint-Gobain or other ones, they have literally thousands of options because it's just...
Another note.
Yeah.
Go back to that last slide.
Yeah.
There's a little British publication that's floating around that talks about the pluses and minuses of different passive shading devices on the exterior building. It's actually quite good.
Oh, yeah. Cool.
And it doesn't matter if it's Northern Hemisphere, Southern Hemisphere. It's a UK piece of literature.
Yeah, you just got to swap north and south.
It talks about cost benefits and ease of building and all that sort of thing. So it's quite good at a residential level.
Yeah, absolutely. Absolutely. Is glass generally the cheapest?
Pardon?
Is glass...
No, I'm talking here about like sun shades, different types of sun shades, or blinds.
Oh, comparisons
external,
between
internal,
them.
within, all that sort of thing.
Cool. Cool. Yeah, I like it. I would generally recommend exterior blinds if possible, but interior blinds will help. But the interior blinds, they heat up in the sun, but they're already inside. Must say that, yeah. But yeah, lots of cool things. Changing out the gas inside, argon gas. I feel like most of the windows that are supplied here have argon inside them. It makes a difference, but not a gigantic difference. The coating and the size of the glass, I think, are the most important. But yeah, overheating. Okay, yeah. Did I put in the wrong one? There it is. Oh yeah, I forgot to delete that one. Okay, so roof assemblies, different ways of building, just kind of going through some options. A warm roof, a hybrid roof, a cold roof. Cold roof is fairly typical. This is a skillion cold roof. To get R6.6, you need to put kind of 2 layers of it just to get your R6.6. You can get R6.6 out of one warm roof assembly. That's about 120 mils of insulation, I believe. Don't quote me on that, but I think somewhere around there. You could do hybrid as long as you're doing 2/3 to the exterior and 1/3 to the interior. We're back. We're good. In Auckland, you can kind of stretch that to like 50-50, R value outside to inside. Oh, we're starting to be silly now. Do I have to unplug and replug? Yeah. Let's go with this one because that's what worked last time. But yeah, different ways of building things. With the cold roof, a metal roof, I tend to also ask for changes on that because a typical cold roof that you would see in E2AS1 has metal roof underlay hard up against that metal roof, and then a big attic gap, and then ceiling insulation. Like I said, with night sky radiation, you get risk of condensation on the underside of the underlay. So it's inside your building and it's touching the rafters. If you put a gap between the metal and the underlay, like I've shown there, you get some drainage through there, but you also get a little bit of ventilation gap through there. But also, the key thing is you're not getting condensation to the underside of the underlay, you're getting it to the underside of the metal only. And so you don't have to worry about it as much. Airtight membrane here on the interior side to prevent most of the interior warm air from going through and adding to that condensation risk. It's a hard sell sometimes, but yes.
That's because jib is permeable.
Jib is permeable, vapor permeable. Your paint layer can work as a vapor barrier, but the things that generally mess everything up are the walls interacting with the ceiling, light fixtures, plugs, whatever holes there might be through the ceiling for services and whatnot. The edges as well is where things tend to crack and you'll start to get air kind of coming through there. So yeah, it's because it's vapor permeable. If it was perfectly like sealed, airtight, and you had a nice thick paint over a wall or a ceiling, it can act as your interior vapor barrier, but generally it doesn't get done to that level because there's always trades coming through and cutting holes and stuff like that. So we tend to recommend assemblies that even once all the rest of the trades come in, even once you have all these holes, it still is bulletproof. It still will work in all seasons, essentially. So yeah.
Sorry, Peter, just at some point, is it worth rounding up this notion of airtightness and all the gaps in the reality of the build? Is airtightness the folly, or you advocate for airtightness plus a mechanized system, or is there a way of airtightness and gaps? And
sure. So I'm going to give a kind of a complicated answer to this. if you are fully air leaky, non-insulated, and just kind of, open to the elements the same way an old villa was,
the old villa.
that works very well.
Yep.
It's not super comfortable. It's not super energy efficient throughout the year, but it works, and it doesn't have a lot of problems, especially because like older timbers were used that are much more durable than radiata pine, et cetera, et cetera. The other side of the spectrum is going fully airtight with mechanical ventilation, with all of your thermal bridges closed, and basically designing to a passive house standard. That other side, that also works very well because you've checked all the ins and outs, you've closed all the gaps, you've made sure it's nice and airtight, and by making it airtight, you're not causing a problem because you're also providing that ventilation constantly. The middle ground is the risky part. And I can't tell you what specifically is going to be the risk. I can't tell you specifically what the failure is going to be because that depends on the weather, depends on the orientation, depends on the specific materials, the specific layout. But by having it mostly airtight, mostly insulated, no ventilation system, no heating system, which is what our code allows, there's a big, big pool of risk there. And sometimes houses, because they're just in the perfect location, perfect orientation, and the people inside are running their heaters at the right amount, perfectly fine and it works. But it's not guaranteed to work. It's not designed specifically to work. It's just, it got lucky. So that's kind of where I look at it. And so I try to push people towards the passive house side of things. I do realize that there's commercial sensitivities involved, and there's complication, and there's upskilling, and there's materials maybe that aren't super well available or cheap. And that's where I try to balance that gray area and try to reduce as much risk as possible, but try to do as good a job as possible. Yes.
So this is why you're going to advocate modelling, because you can model to the specifics of a particular thing.
Yes.
For so many people, they just see that as dollars, and I'm with you, but
I hear you. I hear you. A lot of people see it as dollars, and so what I try to do is, what I've gotten a win on was doing modeling to be able to delete the heat pumps on a very low-cost, subsidized housing building, because the clients were telling us the occupants will never, ever, ever use the heat pump. They might use it a little bit during the winter, but in the summer, definitely they will not be using air conditioning. So I said, okay, cool. If you want to delete these heat pumps, you can delete that cost. You can delete the cost of upgrading the transformer outside and save a bunch of cost on that and save a bunch of complication of trying to find places for the heat pump condenser units outside, things like that. And then they're like, okay, cool, let's do some modeling. And so we did the modeling, we checked for overheating, and then we got smaller panel heaters inside instead of putting a full heat pump, which was much more cost effective to build and install. But we also requested that ventilation systems got put in there so that you constantly had that cycle of air, as opposed to relying on the occupants to constantly open the windows, which, once again, we were told by the client, they will not do that. Some will, but not everyone will. So yeah, when I'm trying to get modeling across the line, I try to find out different creative ways that I can save money on the project and use modeling to justify that.
So when you say ventilation system, like
yes.
a little extract fan?
So when a ventilation system, I'll just repeat it. Ventilation system, it can be a cheap extract fan. So our general recommendation is a balanced ventilation system with heat recovery. So something like a Stiebel Eltron or a Mitsubishi Losnay, or the ones where they have like a heat exchanger on the inside and two fans, one pulling air out, one pushing air in. So that's what I recommend, but those are like $5,000 to $10,000 each. And so if you're putting those into apartments, that's a cost, obviously. The lowest minimum that I generally go with is an extract fan in the bathroom that runs constantly at low speed, and then you flip a switch and you can hear it, and it's like shower mode or whatever you want to call it. Because that'll at least generate some airflow. Ideally, you want to have it going through windows, going through trickle vents, going through some sort of actual thing. But at the pressures that it's going through, you don't have to put anything. It'll just come under the doors. It'll come through the window gaps. It'll come through all those things. So that's what's standard in Toronto, at least. Like high-rise buildings will all have, constant background exhaust, and then you turn on the fan, and then it'll stay on for like 15 minutes or 20 minutes or half an hour, so that after a shower, it'll exhaust all that moisture. But yeah, ventilation is key, because you can't trust people to open the windows. And especially when you need it the most, which is the winter, when it's your interior temperatures and relative humidities are closer to the dew point temperature where you want as much airflow as possible, people want to keep the windows closed because it's cold outside, right? So that's what the ventilation system is generally for. It's for the cold times. Yes.
New Zealand,
Yes.
What's the extreme balance? How can I phrase this question? What's the extremes of dew point variation? Oh God, I'm not even quite sure how to phrase the question, but it seems to me that you've got to be a physicist to know the answers for all locations in the country, right?
Ah, sure. Yes, there's some nuance involved. There are some assemblies that work pretty well everywhere in the country. There's some assemblies that only work a little bit. There's luckily not a huge amount of temperature variation around the country. Like down, zone 6 down south of the South Island, low temperatures are what, like -10 maybe at a stretch. Whereas here we design temperatures for 5 degrees in the winter up in Auckland. So it's not that much of a difference. The variation in relative humidity, especially in the winter, makes a big difference. Here in Auckland, it's very high relative humidities at high-ish temperatures.
That's
so you
factor.
get, sorry?
That is a factor.
Absolutely, yes. And so with here up in Auckland, sometimes things that would have worked back in Toronto where I come from will not work here because the relative humidity is too high in the winter, whereas it gets super dry in Toronto in the winter. So yeah, I'm not sure. What's the question you're asking in terms of?
So that's why modelling really answers everything, right?
Sure, yes, because you're plugging in the actual climate data for those specific places and modeling it to that specific zone with the specific building, so you can actually get specific answers as opposed to just generalities.
I just realised how inefficient the building code can be.
Yeah. Yeah, it depends on your definition of inefficient, because inefficient, it's very efficient to get tick boxes done quickly and people not having to think very much. But yeah, in terms of getting really comfortable and cost effective and efficient outcomes, yeah, not so great. So yeah, good roof designs. I showed this, I think, last time. Basically just showing, insulation going all the way around the parapet as opposed to breaking at the parapet. Especially if you have this as an open gap from the interior to allow air up into the parapet. You want to make sure there's, some sort of seal between the two. Like this one is also pretty good because you have a nice sealed system over here with your warm roof, a nice sealed system inside the parapet, a nice sealed system on the outside with the cladding. This one as well, nice continuity of your insulation from wall to roof. But some bad roof designs are things like this, where you have the membrane going over onto your brick, and then the membrane shrinks and then pulls the top of your brick and breaks the top there. I've seen some crazy stuff. I saw another one where the brick went mostly to the roof level, and then they just kind of gunked a whole bunch of sealant as like a triangle at the top of the brick. That broke after like a year or two, and then the whole veneer fell off the building, 12 stories, just fell to the ground because it was just deteriorating all the brick ties behind there. Things like this, yeah. So it looks very similar to this one, right? But you'll see that there's a lot of air pathways from one place to another, from the ceiling space into the wall, from the parapet into the roofing, all kinds of things. You want to make sure everything's compartmentalized, because if you're allowing uncontrolled air going from place to place, there could be unintended consequences. At the building science summit that we had, Stein, you guys know Stein from Babbage? He was talking about how he recommends for warm roofs having, what did he call them? I think just compartments. I'm wondering if there was another word. Anyways, basically just having not the whole roof space be membrane, vapor barrier, insulation inside, and then that's the entire roof space. Having stoppages and compartments here and there. So if there's a leak in one area, it'll stay compartmentalized to that area and won't spread to the rest of the roof. So kind of keeps things a little bit separate, which is nice. Yeah. Ideally, avoid the icebergs, and don't believe that it's infallible. Never believe anything's infallible. That's a really key thing. That's the takeaway that I got there. But for roofing, NZBC E2 drainage, make sure the water gets away. Don't be afraid of internal drains. I feel like there's a big fear of internal drains I like them because I'm used to them coming from Toronto, because if you don't have an internal drain, you have to add heat tracing to the drain on the outside to make sure it doesn't freeze up over the winter. So that perhaps is why I trust it a lot more. But I have seen some really dodgy garbage installs of internal drains, internal gutters, and things like that. And so, yeah, it can be a problem. But if you have someone like us on site making sure that everything's done, you're doing testing, you're putting sensors, things like that, you can trust a membrane roof.
To be honest, it's only a short period of time that the componentry for good drainage, like you've shown there, those outlets, has actually been available. You know,
Sure.
In this country, they've only really been around, I don't know, just maybe 20, 25 years. And prior to that, it was sort of make it up and let the membrane flop into some drain. You know?
Yep. And I mean, hey, I've seen those, and they still work after those 30, 40 years or whatever, but some of them are, really badly installed and just didn't get right. With this type of drain, in Toronto, what I would be specifying is the drain with a big flange of copper or aluminium around it, so that whole flange gets welded into the 2-ply torch-on roof, whereas that's not, you can't even find that here. Same with like nice single piece goosenecks for penetrations for wires and pipes and things like that. Cannot find them here in this country. I should maybe start importing them. Who knows? We'll see. Yeah, maybe not copper. Maybe just go aluminium. Get someone to do that. Anyways, sloping. For membranes, I would say 2 degrees if you can. If you're going down to 1 degree, 1 degree has risk of ponding, and it just looks a little bit bad and kind of increases the risk a little bit. It's not a deal breaker, but I recommend 2 degrees. For metal roofs, I generally recommend over 15 degrees so that you can still get that separation between the metal and the underlay, and then have air with stack effect go in there to dry things out. If you're doing it at 3 degrees, it'll work, but if there's any condensation, it kind of just sits. So generally 15 degrees is what I recommend, but 3 degrees I've seen all the time. I've had a bunch of projects like that. It is what it is. There's specific reasons why that's necessary. Walls, lots of external insulation here. I recommend it. Has anyone used external insulation? Yes. Cool. Nice. Yeah, it works really well. In Canada, it's very popular because you need a good amount of insulation. And especially for high-rise buildings, if you're building with steel studs are terrible for thermal bridging. So putting external insulation closes those bridges and makes sure all the insulation's on the outside of that, instead of being deteriorated by like 60 or 70%, putting it between the studs. So yeah, it tends to be very popular for high rises in Toronto, Canada in general. It also closes up slab edges as well. It'll insulate the whole thing and become one big wrap around the building. I like it. I think it's great. I think it works really well, but sometimes council needs a little bit of hand holding, a little bit of head petting to tell them everything's going to be okay. With timber framed walls, great. Internally insulated, it's fine, it works. I always recommend a membrane on the outside just because it's easier to detail penetrations, slab edges, this, that, and the other thing. It also, I've been told by contractors, comes out to be almost equivalent to a board and a tape. So if you're using jib weatherline with tapes versus jib weatherline no tapes and a full membrane on the outside, by the time you add up all the labor and materials, it's about cost effective as putting a membrane, but the membrane gives you a full, membrane over the whole thing adhered. Which works pretty well. And then this one's the other one. So if you have concrete, precast or otherwise, I recommend putting one continuous layer of rigid insulation that is vapor tight, vapor closed. It could be a PIR, it could be an XPS, taped seams, and then all the straps go on the interior side of that. You have a little service cavity, and then you have your gypsum board inside of that. It's not amazing. External insulation is much better because it'll keep your concrete nice and warm. Your warm concrete stays happier, it stays more durable, it's more protected. But if you're having concrete on the outside, sure, it is what it is. And then just make sure you have rigid insulation that will not allow the interior air to touch that concrete. That's pretty good. Good wall designs, yeah, external insulation again. External insulation. This one is one of those insulated precast concretes. Has anyone used those before? Yeah, maybe. Cool. It works pretty well. It's decent. Sometimes it's a bit more complicated to install. Sometimes there's weird leaks that happen because water will get into a joint and then find its way somewhere else. But most of the time, it's pretty good. How to design a precast wall. We have stuff on our website in case you want to go look at that. Bad wall design. This one has lots of steel studs all over the place. This has like nothingness over here. I'm not sure what this tape is. But yeah, just kind of a little bit messy, not very well, doesn't work very well thermally because of the steel studs. And yeah, this detail over here for the window is like fine, pretty standard. This one, yeah, we have a gigantic slab edge thermal bridge, which is not amazing. And then you have your internal insulation there, strap and line, not so good. So you're going to have very cold floors there. You could get condensation underneath your carpet there because the carpet will insulate and then keep the underside of it colder. It's just not great. Not amazing. B2, exposure zone, things that you tend to see. Like this is an older polyurethane or a hybrid. 100% silicones tend to last a lot longer in the sun. They're less paintable, but you can find ones that are paintable. You could also find them in different colors to match whatever you need to match, but they last. Like I've hung on the outside of a lot of older buildings. If it's a silicone sealant, you can still press it. It's still nice and flexible, which is what you want to accommodate that movement. Whereas the older polyurethanes and hybrids tend to get alligator skinny and eventually start to crack, which is not great. E2, yeah, 4Ds of weather tightness. That's how I generally design things. I don't really care about E2AS1 details. If people care about them, I will help you improve them. If the contractor cares about it, then I will explain it to them in ways that make sense to E2AS1. But generally, I'm designing from the first principles: deflection, drainage, drying, and durability. Make sure water gets out, make sure it dries out, make sure there's redundancy, and make sure everything's going to be durable. This one in the middle is an interesting one. I got this on one project because of a very specific detail that wouldn't allow the interior sealant joint to be installed on the precast. And so this is what we do in Canada all the time. This is like a standard detail. You have an interior air seal that is installed from the exterior side with a long tube. So that'll be, 50 mils back, 70 mils back from the face of the concrete. And you can see that in the middle here, so it's continuous all the way top and bottom, but then it also has this other little step out here. And then this front seal that's installed right at the front exterior face, that is intermittent, and so you'll have drains. So if any water does get past that first seal, it'll hit this ramp and then go outside. Not typical. Not something that any contractor likes to look at or hear about. So I got it on this one project because of a very specific detail that needed to happen. The thing that I didn't realize that was being misunderstood is they thought that this interior seal needed to be all the way at the interior face of the concrete, where it does not need to be there. That's where you install typical air seals from the interior side. But I found a lot of problems with those because you're doing the joints and then you get to a bracket, a post, an SHS, I don't know, some sort of steel structure, and the person cannot get their gun into there or the nozzle into there to seal it. So we had that problem on this project, and I said, what about this detail? They're like, oh, we can't do that. We don't have nozzles long enough. And I said, okay, what if it's only 50 mils back? And they're like, oh, yeah, of course we can do that. Great, cool. Sometimes you just have to kind of think outside the box a little bit. But yeah, something to think about. It's on our website if you want to look at it, but also feel free to ask me if you have any of these projects. But it's a difficult one to get across the line with contractors because it's just outside the norm, unless they've worked in Canada. Joinery, good joinery designs. What am I showing you here? UPVC is pretty good. This is a thermally broken aluminium. You can see that this thermal break in the aluminium is nice and in line with the center of the insulation. That's good. Same with the UPVC. It's generally lined up with the insulation. Also good.
Peter, just before we move on,
yes,
just a question from online.
Sure.
Can you please talk more about the internal vapor layer? Where does it build up to avoid being penetrated by fixings, lights, fans, etc.?
For the roof? Doesn't say.
I think he's talking walls, doesn't he?
Might be for walls, yeah.
Let's do both. So I'll go back to the roof designs over here. So for the roof, if you have a conventional cold roof, your vapor barrier will be in this line here, down at the bottom near the warm side of the wall. If it's a hybrid, sometimes it's like right in the middle there where you have your plywood sheathing, let's say. If it's a warm roof assembly, you don't need an interior vapor control or air control layer because your exterior vapor barrier at the bottom of the insulation, that does all the work. And then you're assuming that the rest of the interior space underneath that insulation is at interior temperatures, therefore above the dew point temperature, therefore not causing condensation. And the same thing happens on a wall. So for a wall, what you have external insulation, exterior insulation, that pink membrane right there, that's a fully continuous watertight, airtight membrane. And that works well enough to control condensation inside your wall cavity because you're keeping the wall cavity nice and warm. You're keeping it at interior temperatures. When you have something like this, I can zoom in on there. So this is a typical wall that you would see in New Zealand, other than the fact that there's these extra battens here. I think the new brands details have shown something like that. Usually those battens are horizontally oriented. So you have vertical studs and horizontal straps. You would generally put your vapor control layer at that point so that you have a service cavity so that you're not constantly having to tape around every penetration. You can delete that whole service cavity, but then your vapor control layer would be right behind your gypsum board, and so you'd have to somehow cut a larger gypsum board hole, put your penetration through there, tape around it, and then gypsum board again around it. It's not really doable, but there can be ways to work around there. So yeah, that's that. And then with this one, for your concrete, your vapor barrier is at the interior side of that insulation where the tape is. So if it's a PIR that's foil-faced, the foil face is that vapor barrier, and it's going to be airtight to make sure that your interior air doesn't touch the cold concrete. Hopefully that answers the question. Cool. I got a little bit more time, got 10 minutes. Do you guys have any other questions? I'm just going to kind of skip through some things. Bad joinery designs. This is one I've seen a couple times. Putting an opaque wall behind a window. Don't do that. Please don't do that. If you want to do that, make sure there's a back pan from the joinery manufacturer that has insulation in the back pan and it's airtight and sealed, because this is just asking for condensation to start building up down here. For this one here, yeah, this is another example of that. It's just like, gypsum board and then glass on the outside of that. Please do not do that. Do not do that. You'll start to burn the gypsum board because sun's coming through there. You're going to get condensation in there. Just put a back pan. Do it the way that the window manufacturers want you to design it. This one's an interesting one. This one is one that you might look familiar to you, Ed. But yeah, double windows. Certain projects have double windows because you don't want to have the interior occupants being able to touch blinds and things like that. So this was a double wall. The original detail that came from the supplier, I believe, had two separate windows, and then they weren't really considering much about the timber walls on the interior side of that. But you can see there's a big gap here and a big gap there, meaning that any air that's going through that wall goes into your cavity, and then you'll start to get some condensation on the interior side, especially on this window, because this will provide some thermal performance. That interior side of the glass will be cold because of the cold exterior, and then you'll start to get condensation. Don't do that. Make sure it's nice and sealed. This whole window rough opening is fully sealed, so you're not getting uncontrolled air just going wherever it wants. And then you install your two windows outside of that. I think we had to put also some desiccant in the sill there to make sure that the interior of that cavity stays nice and dry. But yeah, worked pretty well. But just things to consider. Bad joinery designs, yeah. So this is what's showed in the code. This is showed in E2AS1. I try to change this all the time. The reason I try to change this is because this right here, this is your aluminum window frame. That's your timber trimmer. This is generally unsealed, except it has staples, which provide your air seal. I don't think staples are very air sealed. Basically, you just have a piece of timber going into a piece of aluminum, and it's stapled on there. So any air that's going from your interior can go to your exterior. Anything from the exterior can go to the interior, especially at the miter joints of those timbers as well, the miter joints of the aluminum as well. Sometimes the aluminum has small joint sealer, but gets brought to site, shakes around on the truck, and then that small joint sealer opens up. And then we have an air seal back here, but that means that air and water can get all the way back here before trying to get back out, which means that's why you see a lot of the timber that's around older windows starts to rot out. That could be from condensation on the window and the joinery going onto there, but it could also be water collecting underneath it and starting rot from the underside or from the top side. So what we generally do is we will pull the windows in a little bit, put the sealant joint, the air seal, over here where the aluminium is, so the aluminium to the window tapes. Or if that's not possible and it absolutely must be here because the window installer must bring the windows to site with the timber trimmer around it, what we'll do is we'll put a bead of tape, or sorry, like a roll of tape between the aluminium and the timber all the way back to that air seal. So just one strip of tape, full perimeter of the window, install it, put your air barrier, and then it'll work pretty well.
Sorry, so you're taping the aluminium to the back of the jam liner?
Correct.
Right.
Correct. So you're not seeing the timber. You're not seeing the tape. It's all behind the timber.
Yeah.
But you're making sure you have an air seal between the aluminium and the timber all the way to the air seal over here.
Yep.
So that you get a nice continuous seal at the corners, at the junction as well. So yeah, little bits and bobs. Oh yeah, here, so that's the back pan that I was talking about. Make sure you have the back pan, and all of your insulation should be at that back pan. If you're adding extra insulation, you could be changing the hygrothermal performance of there, and there could be risk of condensation inside that cavity. Maybe, maybe not. Could do, might not do. I'm just going to skip through here because we have not much more time. Air tightness, weather tightness. Yeah, if you get nice airtight windows, they'll generally be more weather tight unless they were designed to be super air leaky and have lots of drain holes, and then plugging up those drain holes causes more of an issue. We've had some interesting, we do a lot of water testing on site of the windows, and we've had ones that leak, and then the guys go in and they're like, oh yeah, we'll just seal up a few holes. They seal up a few holes and then it starts spraying in because a smaller hole has higher, same volume but higher speed of air coming through it. It carries water with it. Tanking types, PVC membranes. I'm not really go too much through this, but just showing you that there are good ways to do things. Generally, you want to have your insulation kind of covering the outside. Generally, you want your membrane to be outside of your structure. You want to have some redundant water stops. Poor tanking designs. Wet walls. Don't do a wet wall if you can. It's just not good. It looks gross. It smells gross. You have to add a separate little channel drain there and have someone come clean it out. There's ways to design walls for very cost-effective ways to make those dry, like a bentonite membrane, like Voltex from Alco sells it. Voltex works pretty well because it's just like a carpet that has expandable clay in it. Very easy to install. I think it's like $90 a square meter installed, which is, you know, money, but it's cheap insurance. It's much cheaper than having to dig up and excavate the entire basement to try to fix that. Or the other option to fix leaks on a wall are drill holes in the wall and pump it full of epoxy, wait for it to leak again, pump it full more epoxy, wait for it to leak again, pump it full of more epoxy, and you just keep on going for years. Not great. Not great. And you might have a warranty from your membrane manufacturer, but usually there's a lot of exclusions in that warranty that say you have to pay for the drilling, you have to pay for the excavation, you have to pay for this, you have to pay for that. And we'll do the fixing, but you have to do all the prep work, which means I don't really trust warranties because they're kind of just a waste of time in my opinion. They're good. They're nice to show that someone cares, but they're just full of exclusions, and so you don't want to rely on that. Tanking. Yeah, and I guess just to wrap up, some fun examples of retrofits, because that's what I find in this weird economy that we are dealing with right now. A lot of clients are spending money on retrofits, renovations, remediations, and it's just fun to think outside the box on how to do things. So this is an older library, a rare books library at U of T, where I went to school. They had these books there. That's a brutalist building that is just concrete inside to outside. There was no insulation on the interior side of that. This rare books library is kept at 65 or 70% relative humidity and like 24 degrees inside, 25 degrees inside year round, winter and summer. So because of the high temperature and high humidity on the inside, In the winter, the walls, which are behind those rows of books, was just concrete and getting, exterior temperatures. So on a really cold, like -30 day/night, you would get condensation forming and then immediately freezing. So you'd have all these ice lenses on the interior side of the concrete between the concrete and the books. And then once it went up to about 0 or 5 degrees, which it does a bunch of times during the winter in Toronto, all that ice would melt and then start to leak onto all the walkways below all those books. And they had this guy, really nice guy, that had worked there since it was built in the 70s, going up and mopping up all of the water every single day during the winter. And so they wanted to fix that. And what we did was, there was a few other options. This was a school project for the U of T engineering students. I got to read their projects and see what they were suggesting. One of them was heat tracing. What they wanted to do was put like wires on the outside of the building to heat up the concrete during the winter so that it stayed above those dew point temperatures. And I'm like, that's a great idea, but it's a very expensive idea and a lot of maintenance involved. So what we did was we just put insulation. We put boards on the outside of the concrete so that it was reversible, and then spray on insulation. I want to say that much of it. And more fixings, and then brand new precast panels. And you can see, for the trained eyes in the room, this concrete does not match that concrete. And we had probably 17, 20 meetings about the concrete and looking at samples and things like that. It's really hard to match existing concrete. Supposedly it's going to patina or wear to look the same way, but we'll see about that. But basically, yeah, put a jacket on it, and then the condensation stopped immediately. And guy got to retire because he was getting towards the time that he wanted to retire, and we allowed him to do that without worrying, which was nice. Another one is, this is the old First Canadian Place in Toronto. This was the tallest building in Canada. I feel like it got surpassed just recently in Toronto. Lots of Bianco Carrara, white marble on the outside. A couple of the panels fell off the building and fell down to the ground, and they said, okay, cool, we have to retrofit this. And so what they did was they set up a 3-story scaffold, and they started from the top. The bottom level of the scaffold would pull off the old marble, middle would prep, top would install new glass curtain wall. And so basically just over the period of a year and a half or so, they just went down the building, kept everyone inside working, built temporary enclosures on the interior side, replaced all the other stuff on the outside, and yeah, a year and a half later it was done. And full reclad with everyone working. Oh yeah, this one was also, we did all this with people still entering and exiting the building, didn't have to move the books out or anything like that. That's why external insulation sometimes is a very good option for retrofits, because you can keep everyone inside and just insulate the outside. This was down the street from where I used to live. That's an old precast building right there. Lots of precast stuff on the outside. What they did was they stripped off the precast, built an exoskeleton on the outside of it and a platform on the top of it, put curtain wall up to there, and then built another 25, 30 stories on the outside of it, which is wild to see it going up. But once again, all the people working in that building stayed working in that building. They put temporary enclosures, pulled off the precast, put on the new glass, and then got rid of the enclosure. And so, yeah, didn't have to move anybody out, retrofit, and extended the building, like put another 2/3 onto the building above it. So, yeah, pretty cool. And it's just showing that things are possible if you think outside the box.
Must have been good foundations.
Yeah, definitely. Although I feel like they might have had to go in and underpin. They might have had to go put extra piles on the outside of the building to attach the exoskeleton to, possibly. I haven't looked that deeply into it. I probably should now that you mention it. What value we provide? I already told you about all this stuff, but it's here again. In summary, enclosure engineering, it's about durability, comfort, energy efficiency, ideally at the lowest cost. But what it really is a balance. And we're trying to work in that gray area because there's not a lot of specific standards that tell you exactly what's going to be better than another thing for every situation. It's all very nuanced. And sometimes it's accepting some poor things while getting some other good things. It's sometimes accepting a little bit of compromise in one specific area, but then getting really good gains in another area. Compliance doesn't necessarily mean done right. It can magically work. Like a broken clock works twice a day, or is right twice a day. So yeah, sometimes just doing the tick boxes can get a good building, but it's not designed for that. It's not specifically, made to do that. If you follow the code objectives, like the functional requirements and things like that, things will work because you're doing what the building code is telling you to do. If you're following the acceptable solutions, there's probably going to be some nuance lost, and there's going to be some things that don't actually work. Verification methods usually achieve the objectives, but in certain places, there's some missing links and some incongruities that just won't make that happen. Using Passive House Planning Package, PHPP, to check them usually does pretty well. Condensation is a bigger issue. A lot of people don't want to talk about it. A lot of people don't want to hear about it, but it exists. It's still there. It's still going to work. It's still going to happen. So you should design around it, and happy to help in whatever way you need. We could build better, but it's an uphill battle because you will get arguments because the easiest way is the acceptable solution because council understands the acceptable solution, and that's what they're used to. It's going to be a little bit of a fight to get things done. But it has been done. It's not too hard. It's not too expensive. It's just different. And it will take convincing of a lot of different people. Sometimes people who you think are completely on board and then all of a sudden switch on you. And they've had something that has burned them in the past and they don't want to trust it again. So it could be anything. But think outside the box. Get clever. Travel. Research outside. Go see how things are built in other places. I do that. I go walk around cities and just look at how things are built. But yeah, where can I find out more? These places, Passive House, if you want to do that. Buildingscience.com is pretty good. Lots of great info on condensation, detailing, modeling. That's from one of he wasn't my professor, but he did a guest lecture. Joe Stiebrick, in case you've ever heard that name before. That's his website. His daughter has an Instagram account, Building Science Fight Club, I think, in case you want to scroll and see that. A little bit better. But RDH, we had Brian from RDH come in to talk at our conference. Their technical library is really good. There's a lot of really random things that they have tested that you wouldn't even think could possibly have been tested. I think one of them was how much water will hit a wall based on the size of the overhang and based on prevailing winds and just general physics, I guess. And then they tested it to see if their modeling and their math was correct, and it was. For external insulation, in case it seems scary, or in case you're getting an argument from a council person or from someone else on a project team, they have a test showing that the external insulation, even if you take all the cladding off, it will still protect most of the water from getting through that insulation to the sheathing line. I think ProClima has done some testing on that for New Zealand specific stuff as well. But the RDH library has just heaps and heaps of things. For us, I think that's a QR code for our website. Our website has a bunch of stuff on it. If you have any questions, feel free to email me, call me. Try not to call me 5 times a day, but if you have any questions, I'm happy to answer questions just for free. If I have to write you things or sign things, then I have to charge you money, unfortunately. But yeah, our website has lots of stuff on it. We have a YouTube channel with a bunch of stuff on it. You might have seen me scrolling through social media. We had a big push and there was a lot of things. So weird for me, but good for you, I guess, because there's going to be things to learn. But yeah, I think that's it. Thanks. Thank you. Any other questions from online?
No more from online, but one says, thank you for the presentation.
Okay.
I appreciated the good and bad examples you walked through.
Sure. Hey, I'm happy to provide more. I just, found some things and added them there. But yeah, I've got lots of horror stories, lots of good stories as well. Any other questions, even if it's project specific? Yeah.
I am generally interested in what is your scope of work generally. Is it reclads? Is it new builds? Is it buildings over 12 meters high?
Sure.
Residential, commercial?
Yes, and yes. We do all the things. Generally, the ones that you guys are forced to work with us on are things that if you go into the AC 1827 document and you add up all the risk scores or whatever, and it's above 10 or above 15, then you have to work with us. So that usually is anything above 10 meters, anything that's a bit more complicated, anything that has some new cladding, new roofing, something weird that the council doesn't understand. They might ask for a peer review or a PS1 from us. We've done schools, we've done hospitals, we've done high-rise residential, we've done commercial, we've done big industrial warehouses, basically literally anything, because the physics are all generally the same. My recommendations might change slightly. So if it's like a warehouse versus residential, I might say, yeah, you can put this type of roof on a warehouse because you're always able to see the underneath. You don't have, ceilings in the way, stuff like that. But like generally, most of the concepts I'm going to be recommending the same either way. The ones that we tend not to work on are smaller single-family houses with group home builders. They're not forced to work with us. They don't want to pay the money for us, so they don't. We've had a couple group home builders come and do like info sessions and little workshops to like, oh, look at our drawings, give us some ideas. And so we've done a little bit of that. But we've also done some work on some really fancy mansions, especially down near Queenstown, Arrowtown, Wanaka, up north, like the golf courses near Mangawhai area, bunch of those fancy houses. With the fancy houses, we've been called kind of after the fact when there's problems to find out leaks and why they've leaked. And it's usually fairly easy. Usually it's just very cutting edge, fancy design, and the installers don't understand the severity of what they need to do necessarily. And so there's usually some easy answers. But after working the first few times with a contractor or with a developer, then they'll usually call us back to avoid those problems next time. And so we get called earlier and earlier in a project schedule, which is good, because the earlier we can be there, the more value for money we can bring. Yeah. Does that answer the question? Cool. Any other questions? Thoughts, concerns? Cool. I guess thank you very much to everyone online then. Thank you.
And just a reminder, if you are joining us online, to register your attendance by clicking the link in the bio. Thank you very much, just to register your CPD.
Cool. Thank you. Awesome.
Thanks, Peter.
Thank you. Very welcome. Yeah, thanks.